Welcome to this lecture series on concurrency, state models, and design patterns. My name is Oscar Nierstros. I'm the lecturer for this course. The assistants are Pascal Gadiant and Mohamed Reza Hazir Pazant. Material for this course can be found on the website listed here on this slide. You'll find numerous resources there, as well as links to the Ilias pages, slides, podcasts, and so on. The lecture slides are available as downloadable PDFs. You will find as well, in addition to the slides that I'm showing, are hidden slides with additional notes that look like this. We won't see any of these slides during my presentation, but when you download them, you'll find additional information which may be helpful for you when you're studying the material or preparing for the interactive sessions. This course is going to be organized as a kind of flipped classroom, so all of the lectures, or most of them, will be available as podcasts. You'll be expected to follow the podcasts and look at and study the lecture slides in advance of a weekly meeting, which, depending on the state of the COVID pandemic, will be either a live Zoom sessions or will be in presence in a classroom. Today, I'm presenting a quick introduction to the basic concepts of the course and what we'll be covering in the rest of these lectures. So first I'll give you a very brief overview of the course. Then we'll have a quick look at what we mean by concurrency and how it differs from what we mean when we say parallelism. Then two very important themes that will be running throughout the entire course are those of safety and liveness, so I will introduce those to you quite quickly. Finally, there are many different ways of expressing concurrency in programming languages, and we'll have a quick overview of some of these mechanisms and techniques that we found in programming languages historically up to the present day. The goals of the course are the following. First of all, I want to introduce to you the basic concepts of concurrency, so safety and liveness and fairness, of course. I also want to show you that in order to build correct concurrent programs, we need some reasoning tools. We'll take a very deep look at one of these, namely label transition systems, or LTS, and some tools that support it. And in addition, we'll look at some other techniques, particularly Petri nets, in one of the lectures. Second of all, we'll see that in order to build robust concurrent programs, it's very useful to understand what the best practice is in these programming techniques. These are formulated in terms of idioms and design patterns. And finally, we will get some experience with these techniques. In addition to the regular lectures, the flipped classroom lectures, we will have two sessions which are dedicated lab sessions. So instead of a podcast and a flipped classroom discussion, we will have 2 hours dedicated to a lab twice during the course, and you will work in teams of two solving various programming problems that are based on the material you'll have seen up to that point. Here we see the outline of the course. So here we are today at the introduction. Next week, we're going to dive into how concurrency is supported in the Java programming language. And then we'll proceed and have a closer look at safety and synchronization. We'll also dive into some design patterns which are intended to guarantee safety, and also look at how transactional memory can help us to build safe designs. Then we'll also have a quick look at liveness and how guarded methods can be used to ensure liveness in concurrent programs. Then we'll have our first lab session, which will consist of 4 programming exercises that are based on the previous lectures. As you'll see in the lab sessions, you won't actually have to program very much, but you'll be given an existing concurrent program which doesn't work correctly, and you'll have to use the techniques and design patterns that you've learned in order to fix these to make the programs live and safe. We'll continue then by having a look at how asynchrony plays a role in building live programs, and we'll also see some other techniques, particularly condition objects. And then we'll have a quick look at fairness, and then the second lab session. At that point, we'll switch gear a little bit and look at some specialized topics. One of these is Petri nets, and another is the topic of architectural styles for concurrency, so at a slightly higher level than design patterns. Then there will be a final lecture, the topic of which is still to be announced. The exam will be during the regular semester and is planned for December 22nd. We'll be using two main textbooks for this course. The first is by Doug Lee. This is Concurrent Programming in Java, Design Principles and Patterns. It's a classic in this area and really describes state-of-the-art in design patterns supporting concurrency. On the other hand, I also want to introduce to you some reasoning techniques, and here there's a classic textbook by the two Jeffs, Jeff McGee and Jeff Kramer, called Concurrency, State Models, and Java Programs. And here in particular, we'll see how the label transition paradigm can be used to help us reason about correctly functioning concurrent programs. There are, of course, other books which are interesting, and we'll refer to them occasionally, but we won't be going into them in any depth. In particular, one very interesting book is Java Concurrency in Practice by Goetz and colleagues, which dates from 2006. Next, we'll have a look at some of the basic concepts of concurrency and parallelism. This article is a classic. It's quite old now. It's nearly 40 years old. It's available on the internet from the course webpage, so it's downloadable from there. If you have difficulty accessing us, contact me or the assistants through the Ilias question and answer forum, and we'll make sure that you can access it. So Anders and Schneider provide a very nice classification of concepts of concurrency, and this will form the basis for the rest of the lecture today. So first of all, we can think of concurrency as follows. So a sequential program is a program with a single thread of control, and the execution of such a program is called a process. A concurrent program, on the other hand, may have multiple threads of control, and these can be executed as parallel processes. The question, of course, is how do you execute a concurrent program? And there are different ways of realizing that. So you can execute a concurrent program either with the help of multiprogramming, multiprocessing, or distributed processing. So with multiprogramming, you have processes that share one or more processors. With multiprocessing, each process runs on its own processor, but with shared memory. And with distributed processing, each processor runs on its own processor connected by a network to others. Nowadays, so when this material was first presented, most computers that were available had just a single CPU. Nowadays, any computer that you buy will typically have multiple CPUs and or GPUs. So that means when you're running a concurrent program, it may or may not be making use of multiple CPUs. In some cases, you have programming languages which are available that are aware of the multiple CPUs and have a runtime system that can exploit that. And others basically still assume that they're just on a single CPU, and the concurrency is essentially simulated by sharing these, having these processes share a single processor. It really depends on the implementation. For the purposes of this course, we're not so much interested in parallelism. So we're interested in how concurrent programs are organized and how to reason about them. But we're not particularly interested in the question of whether these processes are distributed, whether they're running on multiple CPUs, whether they're connected by a network or not. Occasionally we'll touch these topics, but that's not the main focus of this course. The main focus of this course is two things. One, design patterns that help us construct safe and live programs, and second of all, tools and techniques that help us reason about how programs can be safe and live. Why do we need concurrent programs? Well, actually, most real programs end up actually being concurrent, at least in some limited ways. So we need concurrency, for example, to support reactive programs. Basically, any program that has a user interface has implicitly multiple threads, because the program needs to be able to listen to input from the user or from multiple hardware devices. You want to, here in such a case, minimize the response delay and maximize the throughput. Another area is real-time programming, where you need concurrent programs to manage process control applications. So you're actually managing multiple devices and you have hard real-time constraints. This is not so much a topic of this course. Another domain is that of simulation. Here we're interested in modeling concurrency which is inherent in our real-world application. So the fact that the real world is concurrent and has many things happening at the same time will be reflected in our programs, because we'll then have to simulate or reflect the real world concurrency that is out there. We already mentioned parallelism, so the goal of parallelism is typically to speed up execution by using multiple CPUs. This, of course, is very important, but is somehow orthogonal to the question of concurrent programming per se. So it's not particularly a topic of this course. And finally, there's the question of distribution and networks, which is out of scope for this particular course. But of course, many of the concepts that we'll see for reasoning about concurrent programs are relevant there as well. So there are a variety of reasons why we're interested in concurrency. Okay, now let's have a look at these terms that I've thrown out, safety and liveness, and see how they're defined and what they mean. So there are various difficulties and challenges in building concurrent applications, and basically four of the key topics are safety, liveness, non-determinism, and runtime overhead. So with safety, we're concerned with the fact that multiple concurrent processes compete for resources. And if we're not careful, they can bump into each other and end up corrupting data. So if each process assumes it's running as a single-threaded program in isolation from others, but then is accessing shared data, it may make assumptions that are not true. So in such a case, you can end up with corrupted data. So safety, in essence, says we don't want anything bad to happen. Liveness, on the other hand, has to do with making sure that all of these concurrent competing processes, if they are being synchronized in some way, that they end up being able to all make progress. So particularly, we don't want that some of these processes end up starving because they can never get access to the resources that they need. In a worst case scenario, you may even have deadlock, where all of the processes are waiting for each other and end up getting blocked. A related theme, which is very important in the concept of liveness, is that of fairness. So you not only want to make sure that all processes make progress, but they do so in a fair way. We'll also have a look at that. Yet another topic is that of non-determinism. If we have a number of processes that are competing, if we run the same program multiple times, it may be that due to random effects that some processes end up running quicker than others at different times. And in the end, the final result may or may not be different. Notice that non-determinism is a two-edged sword. So in some cases, we want to be sure that no matter how many times we run the program, we always get the same result. On the other hand, particularly if we're simulating the real world, we may in fact want non-determinism. And we want to make sure that if we run the program multiple times, we don't always get the same result. So it's not simply a case that non-determinism is bad. It may be good in certain cases, particularly if we're trying to really model randomness. And a final topic, which is important, is always in the background, the elephant in the room, as it were, is runtime overhead. If you are building a program as a concurrent program made of many processes, in contrast to a single-threaded process, you have additional things to do. You have to create these threads, these processes. You have to switch context between them. You have to synchronize them and communicate between them. And all of these things may not necessarily have much to do with the original computation that you want to do. So they're going to cost more. So there's an additional overhead which is appearing, and you want to keep that overhead to a minimum. Now, here's a slide that I'd like you to have a look at. I'm not going to discuss it in any detail now, but when we have the interactive session, we're going to come back to this slide and have a closer look. So here I have some pseudocode. The parts in red curly braces, those are assertions, so they state what we expect to be true at a certain point. So initially we have a variable called x whose value is 0. Then we have two processes, P1 and P2, and each of these processes does something with x. The first one takes x, adds 1 to it, and assigns that value to x. The second process adds 2 to x and assigns that value to x. Now the question is, what's the final value of x? So first of all, what is the intended final value? Do we expect that to be deterministic? What do you think? And second of all, if you can imagine all possible interleavings and assumptions about these processes, what are the possible values that x may take on after executing both P1 and P2? So have a careful look at that. It's pretty clear that one possible thing that could happen is that we simply execute P1 and P2 sequentially, so in one particular order, and the result is x equals 3 at the end. And perhaps that's the intended final value. But there are all sorts of other things that can happen. So how many possible values can you imagine getting for x in the end? So once again, safety. Safety means ensuring consistency. So in our little example there, we may want to make different assumptions about what should be true about x. In particular, what level of atomicity do we expect that the processes P1 and P2 may have in accessing x? So what do we consider to be atomic in such a program? The safety property is essentially one that says nothing bad happens. As we'll see in a couple of lectures, we'll have with LTS and the tool LTSA a way of expressing what safety properties are for programs. And it's a very nice tool for reasoning about the possible states that you may reach in a concurrent program. In the context of safety, we have a couple of very useful concepts that can help us ensure safety. The first of these is mutual exclusion. So mutual exclusion says that during a certain time period, I assume that the resources that I as a process need, I have access to exclusively. So nobody else has them while I have them. And in essence, while I have them, I can update them atomically. So for example, if I'm process P1 and I want to do something with X, I can assume for some period of time that I have mutually exclusive access to X. So while I have access to X, nobody else does. The other is condition synchronizations. So in this case, this is a tool that allows us to express what conditions should be true for us to access our resources. In particular, if the resource is in the wrong state, we may be delayed. The classic example that we'll see, and we'll see this multiple times, is suppose that I have a process that wants to read from a buffer and another process that's writing into that buffer. So this is like a queue of messages that are being sent from one process to another. If that buffer happens to be empty while I want to read from it, well, there are different things that I could do. I could keep checking if there's something in that buffer, or I could simply say, wake me up when there's something in the buffer. So this is conditional synchronization. Say, I'd like to read from the buffer, assuming there's something there for me to read. And if there isn't, I'll go to sleep. So this is a very useful concept for synchronizing processes in a safe way. Liveness is a way of ensuring progress. So if safety says nothing bad happens, liveness says something good happens. Now, consider the most trivial way of ensuring safety. If I have multiple processes trying to access shared resources, I can trivially make this program safe simply by not letting any process do anything. Some bureaucracies, administrative bureaucracies, work like this. To ensure that nothing bad happens, they simply make sure that nothing happens at all. You may wait a long, long time until you notice that there's nothing happening in the world. But of course, this is not what we want. We would like a world in which our processes are able to do work in a safe way, but they also all make progress. A couple of particular special cases of liveness is making sure there's no deadlock. A process is deadlocked if it can never access a resource. In particular, a collection of processes may be deadlocked if they're waiting on each other. And this is certainly something to be avoided. As we'll see a few weeks into this course, there are a number of different ways of thinking about deadlock and ensuring that deadlock doesn't happen, or detecting it when it does happen and fixing it. Another important property is no starvation. So all processes can eventually access shared resources. So it may be a case that we don't have any deadlock, but for some reason, due to bad timing or to bad priorities, some process gets starved out. Think, for example, if you're in a roundabout and you want to get into the roundabout, but there's so much traffic coming from the other direction that you never get a chance to get into the roundabout. So you'll eventually get starved out. So because your priority is to those on the roundabout, if the roundabout is always full, you get starved and you can never get into the shared resource. Okay, we've had a quick look at safety and liveness, but we haven't seen how to create our concurrent programs. Today we're going to stay pretty abstract, so we're not going to look at any actual code. We'll do that starting next week. But today we're going to base ourselves on Andrews and Schneider, and we'll see how historically in programming languages a variety of different techniques have been proposed and used to express concurrency in different programming languages. First of all, you need a way of expressing concurrency. So you need mechanisms to create processes, to communicate between processes, and to synchronize these processes. So we'll take each of these in turn and see what techniques have been proposed. As I said, this article by this tutorial survey by Andrews and Schneider is quite old, but what they talk about there is still relatively up to date and expresses what you'll find in most programming languages today. First of all, there's process creation. How do you create new processes? So traditionally, there have been three approaches, the second of which is the most common today. These are coroutines, fork and join, and co-begin, co-end. Coroutines are a very important historical technique to express a pseudo-concurrent behavior in a program by having multiple coroutines which explicitly pass control to one another. So in particular here we have visualized a program with two coroutines, coroutine A and coroutine B, and the program can call coroutine A, coroutine A runs for a while and then it calls coroutine B. But coroutine A is not finished. Coroutine B, instead of returning, at some point says, oh, well, A needs to do some work. So we'll let A resume. So this is an explicit handover of control of the CPU to the other coroutine. A continues running and then explicitly transfers control back to coroutine B and lets it resume. At some point, coroutine B has all the pieces it needs and it returns. So it returns to the original caller, the program, with the final result. This diagram here is just a sketch. So the actual mechanisms can vary. Nowadays, you won't see coroutines really in programming languages, but you may find them in assembler libraries. So its coroutines are still a way of providing at a very low level in assembly code, a way of simulating higher level processes. Then typically what will happen is you will have in your programming language higher level mechanisms for expressing concurrency. And when code is generated for that, they may be using the coroutine libraries at the lower level. So this is an historical technique, but it's not completely uninteresting because you will find them still in some contexts. The next approach is pretty much the standard today. This is the notion of fork and join. Basically, when you fork, a program is running a particular process. When it forks, it creates a new process that continues executing. So at the point of the fork, you will now have two threads of control. Every time there's a fork, there's a new thread of control that's introduced. In addition to the notion of a fork, there's the possibility of expressing a join. So what join does is says, oh, I'd like to wait until these other processes have terminated. And then once they've terminated, I'll decide what to do next. So for example, here program P1 forks P2, P2 forks P3. At some point, P1 says, okay, before I can continue, I want to check when P2 is done, because I'll need the result from P2. So when that happens, eventually P2 terminates, then P1 gets woken up and says, okay, now the result from P2 should be available, and now I can continue doing what I'm doing. P3, on the other hand, nobody's waiting for it. There's no join on P3, so P3 is independent and continue executing. This is very powerful and very expressive. You can create arbitrary number of processes. It says nothing particular here about how processes are synchronized or how they communicate. We'll see that next. Note, however, that fork and join are rather unstructured, so you have to be very careful in how you program with them. We'll also see next week how fork and join are supported in a programming language like Java, which is pretty classical in terms of how to program with fork and join. For historical reasons, I'd also like to show you quickly co-begin, co-end. This is also rather old-fashioned. It was introduced in the 90s by Edsger Dijkstra. This was at the point in time when people realized that structured programming was a good idea. And instead of having these completely unstructured fork and join, the idea was, well, let's see if we can better structure concurrency by having explicit co-begin and co-end. So here we have a bunch of statements or processes, S1 through Sn, and they will all run in parallel. And when they're all done, they may run at different speeds, then we can continue with the co-end. So the co-end is essentially a kind of a join on all of the processes that have been created. So it's still of historical interest, but I don't think you'll find co-begin, co-end in any modern programming language. So now we've seen how to create processes. The question now is, how do processes communicate with each other and how do we synchronize them? Essentially, there are two broad approaches. The first is based on shared variables and the second is based on message passing. What we see here at the top are processes communicating indirectly. So processes P1, P2, and P3 all are accessing the shared resources X, Y, and Z. So these can be thought of as variables or other kinds of resources or objects that can be read and written. In order to ensure safety, we need explicit synchronization mechanisms to avoid these shared resources getting into an inconsistent state. With message passing approaches, on the other hand, communication and synchronization are bundled together in a single mechanism. So in this particular case, for example, P1 can send a message X to P2. In the process of sending it, P1 no longer has it and P2 acquires it. So there's no point where P1 and P2 can access the resource X at the same time. Similarly, P2 and P3 and P1 can all communicate with each other by sending information as messages. So as a consequence, communication and synchronization are bundled together in a single mechanism. This communication, however, can take various forms. In particular, it could be synchronous, which means that there's a handshake. P1 and P2 both have to be ready when the message X is transferred from one to the other. Or it can be asynchronous, in which case P1 sends a message, it enters the ether, a queue, a buffer, something, a blackboard, and eventually P2 will receive the message X. But the moment P1 has released X, P1 can continue doing something else. And P2 at a later point in time, immediately or sometime later, will receive the message X and decide what to do with it. So here we see that communication and synchronization are bundled together, whereas in the shared variables approaches, communication is indirect through these shared variables, but we need some other explicit synchronization mechanisms to avoid safety issues. Now this diagram here is based on the article by Andrews and Schneider, and I consider it still to be relatively accurate description of what the basic approaches are. So we have on the one hand, we have procedure-oriented approaches, and on the other hand, message-oriented approaches. The most primitive technique is that of busy waiting. We'll see that in a moment. We'll see each of these techniques. So with busy waiting, a process is constantly checking to see if the condition it's waiting for has been fulfilled, that a lock has been released, that a piece of data is available, that there's a message in a queue, and so on. Then, proceeding downwards, we get more and more sophisticated and advanced and higher level mechanisms. So the next approach, which is also a classic, is that of semaphores. So these are higher level locks that can be used to express a variety of different synchronization algorithms. Semaphores are still relatively low level, though they're higher level than busy waiting. Semaphores can be used as a lower level mechanism to implement other higher level mechanisms. On the procedure-oriented approach, we have, as we'll see in a moment, monitors. Monitors are the basic mechanism we have provided in the Java language, and we'll see how they work in a moment. On the other extreme, we have message passing, and message passing approaches where processes don't communicate through shared resources, but explicitly send packets of information to each other. Monitors in Java end up getting mapped to objects. So every object in Java can be a monitor. Somewhere in between, these meet again, and we have the notion of remote procedure calls. So remote procedure calls provide a form of message passing for remote objects. Off on the side, far to the left, we also have the notion of path expressions. Path expressions are a very clean and elegant approach to expressing concurrency, but they're somewhat limited in expressive power. They've made an appearance a number of times over the years, but have typically been abandoned due to their limited expressiveness. Busy waiting is one of the oldest techniques for synchronizing processes. It's very primitive, but also effective. It basically requires you to have a way to atomically test and set a shared variable. As a consequence, it makes it very easy to implement condition synchronization. You simply use this shared variable to set it to signal that a condition is true, and to wait for that condition, you simply repeatedly test. Is it true? Is it true? Is it true? Is it true? As we'll see, mutual exclusion is much more complicated to realize correctly and efficiently. We'll come back to that at a later point in time. It requires a more complicated algorithm. Semaphores were introduced by Dijkstra, the same Dijkstra we heard about before, in 1968 as a higher level primitive for process synchronization. It's a very elegant and clever approach. There are different variants of semaphore, but basically you have a semaphore as a integer valued variable s with two operations that you can perform on it. There's a p and a v. These terms actually come from Dutch because Dijkstra was Dutch. V stands for verhogen, which means to increase in value, and P stands for prolage. That means to try to decrease. So probeer te verlagen. Basically, the idea is as following. At any point in time, you can perform a V, which will simply increase the value of your semaphore S. And a P will decrease the value, but only if that value is not 0. If the value is 0, then P will block and wait. So this is very elegant and simple. You can implement many different kinds of algorithms with this, the simplest being locks. Here's an example of programming with semaphores to implement a mutually exclusive so-called critical section in a program. So a critical section is a piece of code where you want to make sure that you have exclusive access to any resources. So here we have processes P1 and P2, and during their critical sections they want to be sure they have exclusive access to whatever resources they're accessing. And then outside that, they're just doing local computation, so they don't need mutually exclusive access. So it's a non-critical section. So you can implement this in a trivial way using a semaphore, which will give the name mutex, and this particular semaphore only ever has the value 0 or 1. So initially, the semaphore has the value 1, which encodes the fact that the resource is available. Process P1 attempts to acquire the resource by performing a P on the mutex. It succeeds, and the mutex variable goes down to 0, and it can start executing in its critical section. Then process P2 also tries to perform a mutex, but it can't because the mutex is already at the value 0, so it blocks. Eventually P1 gets out and performs a V, releasing the semaphore, and P2 presumably will be able to get in. And then if P1 is very quickly and loops around and tries to access the mutex again, if P2 is still in there, then it will block and wait. So this is a very simple way of using a mutex semaphore to implement a locking behavior. Semaphores, they can be easily implemented using busy waiting, but typically they're implemented at a lower level, either in the operating system or, for example, with the virtual machine in the VM itself. Whereas semaphores are relatively low level and unstructured, you can put P's and V's anywhere, monitors are a higher level construct. A monitor is essentially like a data abstraction, so it encapsulates resources and the operations that manipulate them pretty much like an object. And that's why the Java language supports monitors as the basic approach to concurrency and synchronization. So with monitors, you can invoke an operation, think of a method in Java, just like an ordinary procedure call, and these invocations are guaranteed to be mutually exclusive. In Java, that's only the case if the method is declared as synchronized. We'll see that next week. Condition synchronization is realized using, with the help of the particular operations wait and signal. And these are primitives. And we'll see that Java also supports similar mechanisms. However, there are many different variants of monitors with different semantics of wait and signal. Here's an example. In this example, we have a buffer here. We have the buffer of type T, so it holds elements of type T, where T is any kind of data structure object, and it's declared to be a monitor. The monitor has two methods, two operations, one called deposit and the other is fetch. So deposit puts an object into the buffer of type T and fetch will get it out again. Internally, we have a number of slots, n possible slots in an array, and we have indices, head and tail, which effectively act as pointers within the array, showing you where the first and the last element are, and this loops around. And size is the number of current elements we have in the buffer. In order to realize conditional synchronization, we also have two condition variables, one called not full and one called not empty. Now, because this is a monitor, deposit and fetch are mutually exclusive. However, clearly, when you're depositing something, if the buffer is full, then you'll have to wait. And similarly, if the buffer is empty, then you'll have to wait. How do we realize this synchronization? Well, that's where these not full and not empty condition variables come into play. So the first thing deposit does is it wants to make sure the buffer isn't already full. So it does a not full dot wait. So if it's not full, then we will wait until it is full. Once the condition passes, that means that the size is no longer equal to n, and we can do our work. And then eventually, once we've finished updating the slots by putting the value into the slot at the tail, increasing the size and increasing the tail modulo n, then we can signal on the condition variable not empty. Conversely, with fetch, if the size is equal to 0, which is the case initially, then we're going to wait on the empty, not empty condition variable, which will be signaled the first time somebody deposits something into the monitor. Once this is true, then we can grab the item by looking at the head location in the slots array. We decrease the size because there's one fewer element, and we increment the head modulo n so it moves forward in the array. Then once we're done, we signal not full, so any client who's waiting in the deposit will get signaled to know that there's something actually that can be read. So now these two methods, these two operations can cooperate with each other with the help of these synchronization conditions. As you can see, monitors are higher structured than semaphores. They're still a little bit tricky to program because you have to check these conditions manually. And in the basic version, you can't simultaneously signal and return. A process in the standard version of monitors is temporarily suspended to allow a waiting process to enter, which is not good. The Java version is a little bit different. And then there's some other issues. The monitor state could possibly change between the signal and resumption. So that means that while a process is running, something mysterious may happen to the state of the object while a signal is being executed. If you have multiple signals, they're not saved. And the trickiest thing is so-called nested monitor calls. So if you're using a monitor from within another monitor, this may cause problems that may eventually give you a deadlock. This is something we'll see a few weeks from now. So at the first cut, it looks like monitors are very elegant and a nice solution to the problem of expressing concurrency. In practice, you need to be quite careful in how you use them. So we'll see, on the one hand, we'll have some reasoning tools like LTSA to help us reason about correct implementations with monitors, but we'll also see that there are quite a few design patterns that'll make it easy for us to use monitors in a safe way. Historically, there's another approach known as path expressions, and they're very elegant for certain kinds of problems, but they're a little bit limited in expressive power. So the basic idea is that if you have something like an object with various operations that can only be performed in a certain way, you can express the allowable sequence of operations as a kind of a regular expression. So here, for example, we have a one-slot buffer. Here we express that the buffer can only be used by doing a put followed by get followed by put followed by get. So it's put semicolon get star. This is very elegant, very cool, but you'll see quite quickly if you try to use path expressions for real practical problems, they can get very difficult to use in the end. So historically they're interesting, they keep getting rediscovered over the years, but as far as I know, they're not used in any classical mainstream programming language today. Now let's have a quick look at message passing. So as we've seen, message passing is combining communication and synchronization by avoiding having shared variables. So when you send, the sender specifies the message and also a target, so a receiver. That can be a process or a port or a set of processes, or as we'll see much later in the course, it could be a blackboard, it could be anything. You just say, put this message there. And then the receiver has to express what it wants to receive. So it may have to specify the message variables, possibly the source that it wants, or possibly some pattern to be matched against the messages that are available. So there are lots of different ways of expressing message passing. Furthermore, the message transfer can be synchronous, in which case both sender and receiver have to be ready at the same time, but more commonly they're asynchronous, or they may be buffered. So if they're completely asynchronous, you can send a message at any time, but then of course you have the risk that memory could end up completely filled with messages that no process is reading. Alternatively, you can have an approach in which the messages sent are buffered. So that means that the sender is going to block if the buffer is full. In CSP, communicating sequential processes, and the Occam language, the source and the destination are explicitly named. So this is another example of a buffer where we have a loop here in which the producer is producing items. Here's the buffer, and the buffer at a certain point is willing to receive a value from a producer, and then a short time afterwards it's willing to produce that output for a particular consumer. As can be seen in this example, it's not doesn't match very cleanly to an object-oriented style where we would consider give and take as being operations. Instead, we have a loop which expresses the points in time in which we're willing to accept or send different kinds of messages. So there isn't a very clean mapping between those and operations. With remote procedure calls and rendezvous, this is in the Ada language, you don't need to know the caller identity in advance. So here you can simply say that it will accept a particular message at any point in time, a give message or take message. We'll be having a closer look at these different kinds of approaches and particularly monitors in the coming weeks. For each of these slide decks, you will find at the end a couple of additional slides. So I already mentioned there are note slides, which you will find in the PDF if you download them, that have additional explanations. But you also have 2 slides at the end, which may help you in studying. So in particular, there's a slide labeled What You Should Know. And these are pretty straightforward questions you should be able to answer in a direct way. There's also a slide containing questions. Can you answer these questions? And these are typically more open-ended questions where there may not be a straightforward answer, but based on if you've understood the material, you should at least have an opinion on what the result should be. All of these slides are available under Creative Commons license and can be reused according to the specifications of this license. We'll be meeting each other then after the podcast in the weekly discussion sessions. Please prepare any questions that you have for these sessions. In addition, I'll have demos and questions and discussion prepared for you. See you then.